Hey everyone, and welcome to this explainer. Today, we're going on a bit of a medical detective journey into the fascinating world of clinical pathology. We're going to investigate the exact, almost microscopic mechanisms that keep our blood flowing where it should, and, more importantly, clotting when it absolutely has to. It's an incredible look at the body's built-in emergency response protocols, and we're going to break the whole thing down step by step.
To help guide us on this journey, we're pulling our blueprint directly from a seriously authoritative source. Chapter 11 of the Definitive Textbook of Pathology, 7th edition, by Dr. Harsh Mohan. Now, this isn't just some high-level overview. We're looking at the actual frameworks that pathologists and medical professionals use every single day to understand these critical systems. By following Dr. Mohan's structural breakdown, we get to see exactly how doctors diagnose and treat severe blood issues.
Okay, let's dive into this. Here's our four-part diagnostic roadmap for today. 1. Investigating our hemostatic function. 2. The bleeding disorders breakdown. 3. Blood groups and transfusions. And 4. Hemolytic disease of newborn.
Starting right off with Section 1, investigating our hemostatic function, the first response.
So the term hemostatic function is basically our starting line. Hemo refers to blood, and stasis just means to halt or stop. Put them together, and we are evaluating how the body successfully stops bleeding. You see, in pathology, before you can start looking into all the complex bleeding disorders outlined in Dr. Mohan's text, you've got to investigate this normal hemostatic function first. It's your baseline. You have to ask, is the body even recognizing the injury? Are the right cellular signals firing off? It is a literal marvel of biological engineering, and establishing this baseline is the absolutely crucial first step for any medical detective trying to figure out why a patient is losing blood.
Moving right along to Section 2, the bleeding disorders breakdown. Identifying the suspects.
Now, when this system crashes, pathologists group that failure under a pretty intimidating term, haemorrhagic diatheses. But don't let the medical jargon scare you. The definition is actually really straightforward. It's simply a medical condition characterized by an unusual susceptibility to bleed. When a pathologist sees a patient with a haemorrhagic diathesis, they instantly know that the normal hemostatic function we just talked about, it's broken. Maybe the patient bruises super easily, or a tiny paper cut just won't stop bleeding. The million-dollar question then becomes, exactly which part of the system is broken?
So the crucial point is, when doctors are trying to find the root cause of a hemorrhagic diathesis, Dr. Mohan's text categorizes the primary suspects into three very distinct buckets. First up, vascular disorders. Think of this as an issue with the actual blood vessels, or the pipes themselves. Second, platelet disorders. This is a problem with the tiny cells responsible for forming that very first physical plug in a wound. And third, coagulation disorders. That's a failure in the chemical cascade that actually solidifies and glues that plug into place. Literally every bleeding disorder traces back to a breakdown in one of these three areas.
Let's look a little closer at the two most critical suspects here, platelet disorders versus coagulation disorders. Pathologists have to be incredibly precise in telling these two apart. Platelet disorders involve the blood's tiny clotting cells. If you don't have enough platelets, well, your body can't even start to form that first line of defense. It's like trying to build a wall with no bricks. Coagulation disorders, on the other hand, mean you might actually have enough platelets to form a loose plug, but you lack the chemical clotting factors required to lock it in place permanently. You've got the bricks, but no mortar. Telling the difference between a cellular platelet issue and a chemical coagulation issue is a real game changer because it dictates the entire course of a patient's medical treatment.
Which naturally leads us to a pretty vital question, right? Once we've finally identified the disorder, whether it's vascular, platelet, or coagulation, and the patient has already lost a dangerous amount of blood, how exactly does modern medicine step in to replace it? I mean, identifying the bleeding disorder is only half the battle. Keeping the patient alive is the other.
And that brings us to Section 3, blood groups and transfusions, the medical solution.
Enter basic transfusion medicine. You can't just pump any random blood into a patient suffering from a bleeding disorder. It requires the incredibly critical science of matching blood groups for safe transfusions. Our blood is uniquely categorized, and if a doctor gives a patient the wrong blood group, no way. The patient's immune system will literally see that new blood as a foreign invader and start attacking it, making a bad situation so much worse. Understanding blood groups isn't just medical trivia. It is the absolute foundational key to safely treating those severe bleeding disorders we just investigated.
Finally, let's look at Section 4, hemolytic disease of newborn, when systems clash.
Let's move to and see how this builds chronologically in a real, high-stakes human scenario.
Hemolytic disease of the newborn occurs precisely because of the strict blood group science we just discussed. Step 1. There's an incompatibility, a clash, between the blood type of an expecting mother and the blood type of her unborn baby. Step 2. Because of this clash, if the baby's blood enters the mother's system, the mother's immune system gets sensitized. It basically remembers the baby's specific blood group as an enemy and builds antibodies against it. Step 3. This creates a massive risk, often much more severe for future pregnancies, where the mother's immune system might actively cross the placenta and attack the baby's red blood cells. It's a profound, heartbreaking example of how a microscopic mismatch in blood groups can have devastating physiological consequences. It requires immense pathological oversight to manage and prevent.
So we've covered normal function, the breakdown of bleeding disorders, the strict rules of blood groups, and what happens when those groups tragically clash. And I think it leaves us with this final, lingering thought. If human blood is so incredibly fragile and so uniquely categorized, requiring such precise matching to prevent disastrous immune responses, what future discoveries in pathology might one day bypass these rules? I mean, could we ever see a reality of truly universal transfusions, rendering the dangers of mismatched blood a thing of the past entirely? It is an incredibly compelling frontier for medical science. Thank you so much for joining me on this explainer, and keep questioning the incredible mechanics of the human body.